So, here's my next question for you. What change or changes of state require the largest changes in energy to accomplish? So we know it all has to do with kinetic energy, and how much our state of matter has of that. But what do you think is the biggest change in energy? This could be one or more changes of state. So take a second, discuss with someone near you, write down your answer, and then I will talk about it. So, our options, right, are going from a solid to a liquid, or liquid to solid, and then going from a liquid to a gas, or gas to liquid. The answer is going from a liquid to a gas, or a gas to a liquid. So, boiling and condensation require the large changes in energy. Why is that? Take another moment, think about energies and what's happening, right, and the motion of the particles in each state. See if you can tell me why. Maybe write down why you think that's happening when you're in the book. So, I'm gonna go back a second, right? If we look at this graphic right here, right, going from a liquid to a gas, a liquid is experiencing intermolecular forces, just like a solid is, right? When you go from a solid to a liquid, you're weakening the forces, so that takes some amount of energy. But when you're going from a liquid to a gas, you are completely breaking those bonds and completely overcoming those forces. That's why it takes more energy, a bigger energy change when going between these two states, right? Because you have to completely overcome those bonds to get to a gas. So, now we're going to talk about heating and cooling curves. And these are graphs that can be really useful. We're going to learn how to read them and what they mean. And on these graphs, we have temperature on the left, and in this case, it's in degrees Celsius, and time on the bottom. And in this case, it's in minutes. So heating curves, we're going to start with a heating curve, and then we'll get to a cooling curve. Show how the temperature of a substance changes as it's heated over time. So let's think about water. You hopefully know the melting, freezing, boiling, um, condensating points for water. Um, I want you to fill out this graph for water. So what do you think the heating curve for water looks like? Um, and remember, this is the temperature. We're going to add temperature over time, so the temperature should be going up in some way, right? We're heating up the water. We're starting at negative 100 degrees Celsius, and we're going to end at 200 degrees Celsius. So your first clue, right, is this is our starting point down here, and our ending point will be up here. What do you think this heating curve will look like? What will happen as we add temperature over time? So draw this in your notebook. This one I want you to do just by yourself. And then draw what you think this graph should look like as we heat up water. I will give you, let's take a minute and a half because you have to draw this curve. So pause the video, take a minute and a half, draw what you think this should look like. Okay, so I'm going to show you what the heating curve of water actually looks like. And it is labeled, and then we'll kind of talk about what it means and why it looks that way. Um, and then we'll talk about what you drew. So this is what the heating curve of water actually looks like. You can see here we have sections where the temperature is increasing, and then we have plateaus, right? And then sections where it's increasing, and then we have plateaus, and then sections where it's increasing. Um, I will say most students, when I have them do this, they just draw a straight line, which is a really good guess. That's probably what I did when I was in high school and I did this for the first time. Because it's kind of weird that we have these plateaus, but I'm gonna well, first we're gonna think about it and then I will explain why that's happening. Um, but yeah, I want you to draw this in your notes. So you have this. We have, as it's a solid, right? It heats up. The temperature increases over time. When it gets to, this would be 0 degrees. Sorry, I didn't label this. 0 degrees Celsius. It melts, right? But it plateaus. So there's time spent here where the temperature is not increasing. After all of the ice has melted, the temperature begins to increase again. So it's a liquid here, right? This would be 100 degrees Celsius. At this point, it's boiling, right? And there's an even bigger plateau. And then once it's all a gas, the temperature begins to increase again. So I've got a couple questions for you. The first one, how was your heating curve different from the correct heating curve? So just take 30 seconds to a minute, write that down in your notebook. Um, yeah. So, like I said, a lot of students their first time just draw that straight line straight up, right? That is a totally normal thing to expect. It's a great guess, actually. Um, but now we're going to think about why those plateaus exist. So, my second question for you is why are there plateaus in temperature when the water is changing phase? You can think about energy and forces. Those are my hints. This one, you can talk to someone next to you. So take a moment to pause the video, chat with someone next to you, and then write down your answer. Why are there plateaus in the temperature when the water is changing phase? Okay, so I'm gonna click onto the next slide. It's got the answers on there, but I'm gonna explain each part. So we have this curve, right? This is the same curve. It is labeled a little bit differently now, but you can still think of it as the curve for water. We have number one, which is the temperature of the solid increases. The particles are gaining more kinetic energy. So the ice particles are vibrating more and more, right? When you reach the melting point, right, it's changing to a liquid. The ice is becoming water. We have this plateau, and that is because the kinetic energy is still being added to the ice, right? You're still adding heat, but it is being used to weaken the intermolecular bonds holding the solid together, right? So there are those lattice bonds, and those have to be weakened to the point that they are no longer lattice bonds and the particles can move past each other and become a liquid, right? So the energy that we're adding to the ice is no longer being used to increase the kinetic energy of the molecules themselves. It's being used to overcome those bonds, right? So we get a plateau in the average kinetic energy or the temperature. Once all of that ice is melted and we have water, the average kinetic energy of the system increases again, right? So this would be like 0 to 100. Temperature of liquid increases. Particles are gaining more kinetic energy. And then again here, we are boiling now, so we're changing from liquid to gas. Get a bigger plateau, and the kinetic energy is being used to completely break and escape from those bonds. So the average kinetic energy is not changing because that energy is being used to overcome those bonds and for those particles to escape. This plateau is bigger than this plateau. Why do you think that is? We actually kind of answered this earlier, right? We said earlier that the transition from liquid to gas is the biggest change in energy. That just shows up on our graph, right? It takes more energy to completely overcome those bonds than to simply weaken them. So you have a greater amount of time, more energy needed for those bonds to be overcome. So here's a cooling curve, right? It's basically just the opposite. It's going in the opposite direction. We can imagine this is 100 degrees if this is water, this is 0. Gas, we get condensation here, liquid, freezing here, and then we have a solid, right? So similar ideas as we talk about each of the parts of this graph, right? The very first part, the temperature of the gas decreases, particles are losing kinetic energy. The second part, condensation is happening. We have this plateau. The formation of the intermolecular forces is actually releasing energy, which means we're keeping the temperature constant. That's why we have a plateau. So it's just kind of like the inverse of the heating curve. As it's a liquid, we're taking energy away, so their particles are losing temperature. You get the second plateau, which is the freezing point, and the formation of the intermolecular forces again releases energy, which keeps the temperature constant, and then it becomes a solid, right? Well, kind of the inverse of our heating curve. Um, you are going to look at some of these today as you do some work, and you're going to try and interpret what they mean. Remember that energy and kinetic energy um, are key to understanding these phase transitions. Should always keep that in mind. And that solids and liquids have potential energy, right? They have stored energy in those intermolecular forces and bonds. So this is three things to remember. The theory is kinetic molecular theory, but when we get to a plateau, you can remember that a phase change is happening there, and there is a potential energy change as well. That's why the kinetic energy is not making the temperature change. So remember these as you look at these graphs. Remember that kinetic molecular theory has to do with the motion of the particles and the changing of phase. And good luck on your work.